I'm Dan Levin, and on behalf of my colleagues Marco Canini, Stefan Schmid, Fabian Schaffert, and Anja Feldmann, today I'm going to be presenting our work called PANOPTICON and talking about how enterprise networks can benefit from incrementally deployable software-defined network management. So the management of enterprise network infrastructure, such as the one whose link topology is depicted here, presents numerous complex operational challenges. So the operators who manage network infrastructure like this must quickly and correctly execute changes to the network policy, conduct scheduled maintenance, and a broad array of other tasks without introducing faults or downtime to the network. And over the last few years, we've seen that software-defined networking has emerged or received significant attention as an approach to address certain challenges of network management and operation. In a software-defined network, the conventional distributed control plane is removed from the individual devices and replaced by a control platform that implements a programming interface to the network control plane. This logically centralized control platform realizes an abstraction for network control, namely a global view over which the network control programs can operate. And by virtue of this software-defined interface to the network management, principled approaches to managing or orchestrating the network can be achieved. So indeed, there's been a rich and growing body of work that illustrates how this SDN interface enables principled solutions to challenging network management problems. Examples include guaranteeing strong safety properties during network policy updates, innovation in the network programming languages to enable operators to more effectively express policy, and systematic verification and troubleshooting approaches, and many others. However, all of these approaches leverage an existing software-defined network deployment. And with the exception of a few notable deployments, such as Google's B4 wide area network, software-defined networking still remains an experimental technology for many organizations. The problem is that network operators face difficulty in transitioning an existing enterprise network to a software-defined network and running it as such to the benefit of the operator. And this is not a trivial process. So SDN is not a feature that you can just turn on by enabling, for example, OpenFlow in the switching hardware. It involves a refactorization of the network control plane and management plane, and therefore its deployment needs to carefully consider the interaction with existing network protocols and mechanisms. There's also a chicken and an egg problem. So operators must be able to establish confidence with any new technology before adopting it fully into production. So operators should be able to leverage existing familiar network management approaches and tools throughout the entire transition process, as opposed to performing a flag day transition to the SDN interface. So these realities necessitate an incrementally staged deployment, leading us to a hybrid software-defined network. That is, a network consisting of both programmable SDN switches and legacy forwarding devices. So this reality leads us to three key research questions. The first is, how can we incrementally deploy SDN into existing enterprise networks? The second is, what are the benefits that we can realize from such a deployment? And finally, we want to understand the limitations or performance costs associated with this approach. Excuse me. So to answer these questions, we propose PANOPTICON, which is an architecture to realize incrementally deployable software-defined networks. Our contributions include a systematic approach for designing and operating a hybrid network as a nearly fully deployed SDN, including a scalable mechanism for extending control to legacy switch ports, a prototype implementation to illustrate the system feasibility and demonstrate use cases, and a planning tool to explore the resource performance trade-offs inherent to hybrid SDN deployment. So let's proceed to our first question to ask, how can we incrementally deploy SDN into an existing network? So to illustrate our architecture, I'm going to walk through a simple example. Let's assume that we're given this existing simple network in which we want to realize the SDN interface. In our approach, we can reason about layer 2 and layer 3 switches and routers, but for the sake of simplicity, let's just consider a simple layer 2 network consisting of just the switches and associated spanning tree. The gray links indicate unused links due to STP block ports. So in order to determine how to deploy SDN into this network, we let the network architect specify the set of network access ports to be controlled through the SDN interface. We call these ports SDN controlled or SDNC ports. And these are going to be a recurring thing where we try to satisfy as many of these as we can in the network subject to resource constraints. Potentially, this extends to the entire set of access ports in the network. So next, we take as inputs the network topology, long-term traffic estimates, and a set of resource constraints and performance objectives to which we apply a planning strategy that will provide us with the exact hybrid deployment, namely where to deploy programmable switches into the network. And we'll revisit this planning strategy later when we come back to the evaluation. So based on the outcome of our planning, let's assume that this is the resulting partial or hybrid SDN deployment. So this brings us to our second question, which is, how can we actually realize any benefits from this? So we reason that the main benefit of the software-defined network management interface lies in the ability to principally orchestrate the network policy. So what this means is that you could use the network policy as a fundamental building block to secure the network, verify correct forwarding behavior, and guarantee safety properties. So to realize principled network orchestration in this network, we're going to leverage two key insights. The first is that we note for every path that traverses at least one SDN switch, we can orchestrate the network policy. For example, this can take the form of dynamic access control, or we could redirect traffic to a middle box. The second insight is that for every path that traverses at least two SDN switches, we can realize a more fine-grained approach to traffic control. In this example, for example, we could load balance traffic across these two paths. So now, in order to leverage these two insights, we must first ensure that all traffic to or from any SDN-controlled port always traverses at least one SDN switch. This is a principle that we call SDN waypoint enforcement. Now, notice that the result of this requirement, as a result, certain paths may become stretched. But this is typically not a problem in the context of many enterprise networks, as we're going to explore in the evaluation. However, to achieve waypoint enforcement, legacy devices must be made to direct traffic to these programmable switches, and importantly, we must do so by relying only on the existing mechanisms of the legacy network. So how do we do that? So we begin by conceptually grouping the SDN candidate ports into cell blocks, which are subgraphs of the network that give us desirable scalability properties when we try to implement traffic waypoint enforcement. Within these cell blocks, we direct traffic over what we call solitary confinement trees. And these are simply per-port spanning trees that allow us to force traffic or restrict traffic from SDN-controlled ports to SDN switches. In practice, these can be implemented or realized using VLANs. So this approach allows us to consume one VLAN ID per SDN candidate access port. It allows us to reuse VLAN IDs across cell blocks. And these solitary confinement trees can be pre-computed and pre-installed into the network. They can remain largely static, except for when topology changes may necessitate their reconfiguration. So now that we've achieved waypoint enforcement across these legacy devices, we can finally realize the SDN interface in this hybrid network. Conceptually, PANOPTICON yields an abstraction of a logical SDN that potentially extends over the full network, the fidelity of which is a function of the number of upgraded switches, and it improves as we progressively upgrade more and more of the network. So importantly, this logical SDN abstraction allows the SDN control platform to operate as though it were a nearly fully deployed SDN. Dynamic network management, or policy management, is shifted away from the legacy devices and onto this control platform. So now that I've explained the architecture of PANOPTICON and what it enables, I'm going to explain how we've evaluated our work. So our evaluation consists of network simulations, traffic emulation study, and testbed experiments. And due to time, I'm only going to be focusing on the simulation results, but I invite you to see our paper for our prototype implementation and to see our traffic emulation study. So our simulation methodology begins with device-level configuration data from a real American enterprise network consisting of 1,296 access switches and 412 distribution switches. And for every access switch in the network, we define a candidate SDN-controlled access port on a distribution switch, and these ports will form the access ports of our logical SDN. In addition, we define a traffic workload based on a packet-level trace from the Lawrence Berkeley National Laboratory data set to define a traffic matrix. And we map the source-destination pairs of this traffic matrix over the endpoints of our topology in a prefix-preserving but random fashion. And we scale up the traffic demands so that in our network, the most utilized link is utilized at 50% of its nominal capacity. And this is simply because in the original network, the actual link utilization was quite low. In each one of our source-destination pairs, we simply choose for ourselves that to express the policy of the network, we're going to require, on average, 10 forwarding table rules to express the policy. However, this is a bit arbitrary. I'll come back to why we choose this later. So the next thing we do is we introduce our resource constraints. So in order to actually ensure waypoint enforcement to every candidate SDN-controlled port, we must be mindful of VLAN ID availability. And many enterprise-grade switches support between 256 and 1,024 VLAN IDs in simultaneous use. The flow table capacity in software-defined programmable switches defines the achievable complexity of our network policy. And for our simulations, we assume 100,000 flow table entries available on these programmable switches. However, today, switches with 1 million entries are also obtainable. We choose this because this is something that can be estimated in advance based on the policy expression needs of the network and planned for accordingly. Finally, link capacities must be taken into account when we're accommodating the traffic matrix subject to waypoint enforcement, and these are derived from our annotated network topology. So let's return to our first simulation experiment, and we want to know how many SDN candidate controlled ports can we accommodate as we grow the SDN deployment. So we evaluate two different placement heuristics. The first is a random approach where we just sprinkle programmable switches over the network as kind of a lower baseline. And the second is a slightly more clever heuristic that uses the volume of traffic in the network to decide where to place switches. I invite you to look at a technical report where we present a formal model and an optimization, linear optimization problem that can yield optimal results when you formulate this problem in terms of an optimization problem. We then try to accommodate each of the SDN-controlled candidate ports subject to the resource constraints. And for every parameter that has a random seed, we repeat each experiment 10 times to ensure that we get representative results. So let's first look at the question, how many SDN-controlled ports can be accommodated by this partial SDN deployment under random switch placement strategy? So on the x-axis, we have the number of deployed SDN switches in terms of the percentage of the overall network devices. And on the y-axis, we have the percentage of accommodated SDN-controlled ports. And we look at three different VLAN capacities, 256 up to 1,024. So what's important to note is that as the legacy switches have fewer VLANs, we need more SDN switches to accommodate candidate SDN ports. But the key takeaway message here is that in the optimistic case, we can achieve all of the SDN candidate ports satisfied when we have 1,024 VLANs in our legacy switches, and roughly 6% of the network devices support SDN. So just a purely random strategy, 6% of the network, we can get an SDN interface. But it turns out with a slightly more thoughtful deployment strategy, we can significantly improve our baseline. So by deploying SDN switches into the network locations which handle the most traffic volume, we can accommodate more SDN ports with a smaller deployment. So under optimistic conditions, we can accommodate all of the candidate ports when just 2% of the network supports the SDN programming, switch programming API. Under more conservative, in a more conservative situation, we require closer to 10%. So let's now turn to the second simulation question, where we're asking, what is the effect of PANOPTICON on the traffic in my network? So the first thing that we look at is the utilization of the most utilized link in the network as we upgrade the number of switches in the network. So the first observation is that when you have a very small hybrid deployment, traffic bottlenecks emerge due to the fact that we're waypoint enforcing traffic to just a very few number of switches. But as the number of SDN switches increases, the waypoint enforced traffic can be better distributed. Now keep in mind that we actually scaled up the traffic in the original shortest path routing of the original topology so that the most utilized link is utilized at 50% of its capacity. So what this means is that basically as we get to about 2% of the network, we're approaching the nominal capacity of the original network. So let's introduce another metric. This red line shows the 90th percentile relative link utilization increase. This is given on the right axis. So in a nutshell, what this red line shows is that 90% of the links in the network never exceed their nominal utilization by a factor of 1.9. And if we go back to the 2% deployment feasibility point, we see that 90% of the links never exceed 1.4 times their nominal utilization. Finally, let's bring in the metric of path stretch. So intuitively, as more SDN switches are deployed into the network, traffic can be waypoint enforced without the need to divert traffic as far away from the original shortest path. So turning our attention again to this 2% deployment mark, we observe that we can achieve basically all of the SDN-controlled ports with a 90th percentile path stretch less than a factor of 1.9 and the maximum link utilization below 60%. Keeping in mind, we scaled it up to 50% to begin with. So, to summarize all of our evaluation results, we find that it is indeed possible to accommodate every access switch-facing port as an SDN-controlled port with moderate path stretch and increase in link utilization in some enterprise networks. And under optimistic traffic workload and resource constraints, we can achieve this deployment that just covers, we can achieve this with a deployment that covers, in the optimistic case, just 2%, and in the conservative case, 10% of the existing network. So our emulation results, based on TCP traffic in an emulated network environment, support these simulation results we find. And our test bed allows us to show the feasibility of the system mechanisms and demonstrate certain fault tolerance properties. So in summary, I've presented today PANOPTICON, which is a practical solution to the SDN deployment problem in enterprise networks. Starting from a rigorously planned partial SDN deployment, PANOPTICON fundamentally integrates legacy and SDN devices to let the operators run the network as a nearly full SDN. And finally, I'd like to mention that we're releasing our simulation and planning tool code so that if you're involved with network operations or planning, you can explore how our approach might work for your particular network. And so with that, I'd like to thank you, and I'm happy to take any questions.
Hi, interesting work. It seems like a big trend in the enterprise is to move away from sort of switch SDN towards overlays. Can you talk a little bit about what that means for this? Does this just mean that you can consider everything to be a hypervisor switch and therefore 100%? What are your thoughts on the sort of the overlay alternative?
Sure, this is a good question. Could I just ask what you mean, though, when you say overlay? Do you mean like a soft switch in a hypervisor?
Sure.
Or?
I mean, if you consider the extent of virtualization in a lot of enterprises today,
sure,
then a VXLAN, NSX type situation.
So one of the things that we observe is that when you can deploy the programmability into a VM hypervisor, then oftentimes those switches where you actually, or those locations in the network where you can deploy, these become the preferable places to deploy. However, we believe that there are many legacy networks out there that do not have, for example, the ability to deploy programmable switches in the fashion that you can do so in a data center environment. Additionally, what we're trying to aim for here is a way to describe an approach to build a programmable interface to a network that leverages the existing methodologies and approaches, that the operators are already familiar with, so that they can reason about how the network is going to run during this transition phase. And I think that even in the case where you do have the ability to deploy programmable soft switches, you still may want to use this kind of a staged fashion where you're using kind of the existing mechanisms and protocols to build confidence as you increase the size of the deployment.
Cool. Thank you.
Hi. Nice talk.
Thank you.
So my question is about verifiability and partial deployment. So there's been a lot of recent work looking at basically verification of data plane properties, also verification of control plane properties. But a lot of those seem to depend on having a runtime that operates over a set of switches that's, I think, fully SDN enabled. But I was wondering if you could comment on that. Like if you have a network like this that has some sort of partial deployment, what does that do to the types of guarantees that you can get and assertions you can make?
This is a really good question. So we're thinking about this. So let me try to respond to the question first. So certainly, as soon as you introduce mechanisms that can behave differently than a wire between two programmable switches, this introduces basically more behaviors that you have to account for, and therefore it's harder to make the same kinds of strong guarantees. One way that we've been trying to think about this is by looking at if you can characterize all of the expected behaviors of a particular segment of the network between the strong guarantee and verifiable parts. It allows you to sort of create a set of equivalence classes where you can think about what are the guarantees going to be if the sort of dark part of the network behaves in a certain way. So it's certainly an open problem. We have some ideas about how to approach that. But this is why we would argue it's a nearly fully deployed SDN as opposed to a truly full SDN where you have a complete overview of the entire forwarding state, because you simply cannot verify certain kinds of behaviors. And this extends to troubleshooting as well. So one thing that we've worked on is how would you do something like if you know this network debugger or NetSite or OF rewind, how much visibility do you have? And it's kind of a similar trade-off there. But we see that there's actually some encouraging potential to still be able to reason about the network in ways that you wouldn't have been able to do before.
It's a very interesting set of problems. Thanks.
Yeah, thank you.